Okay, today we're going to start talking about biological chemistry. There are several topics that we need to go over: the structure of atoms, chemical bonds, properties of water, and pH of solutions. For this recording, I'm only going to talk about the structure of atoms, and then I will make other recordings on chemical bonds, the properties of water, and pH. For the structure of atoms, your learning objective is to describe atomic structure. And what I mean by that is you need to know the location and charges of subatomic particles. You also need to know what the atomic number and atomic weight are. And you've covered some of this in your BioBeyond assignment. So first of all, take a moment and think about the definition of matter. So matter is anything that takes up space. Okay, so I'm going to write this down for you. Any material hopefully you can read my writing that takes up space. Okay, so matter is not necessarily living organisms. Matter can be anything, like the desk that I'm working on, a rock outside. So matter is anything that takes up space. Now, an element right here is a substance that cannot be broken down. So elements, if you've ever seen the periodic table, that's a table of elements. So examples of elements are things like carbon, right? You've heard of carbon before, probably. Or oxygen. Hydrogen is an element. And another example is nitrogen. Now, these four elements I gave you as examples are actually the most important elements in living organisms: carbon, oxygen, hydrogen, and nitrogen. Now, the reason that we're talking about elements is that an atom, which is the smallest unit of matter, is actually a type of element. And what I mean by this is an atom has to be a certain element. So we can have a carbon atom, an oxygen atom, a hydrogen atom. Okay, so an atom is the smallest unit of matter that still maintains the properties of an element. And when I say properties of an element, I mean like the number of protons and electrons and how that element acts when it's around other elements, okay, and how it bonds. So I used this image or this animation because I want to show you that there are particles orbiting as part of an atom, and they are orbiting around what we call the nucleus. So take a minute and think about what the three subatomic particles are in the image and what their charges might be. So you've probably heard of these particles before. We have protons, electrons, and neutrons. So there are more than three subatomic particles in an atom, but those are the three that you need to learn: protons, electrons, and neutrons. So when we think about the charges, protons always have a positive charge, and we can abbreviate a proton as P plus, lowercase p. Electrons have a negative charge, and they can be abbreviated as E minus. Now, neutrons do not have a charge at all. Okay? So I'm just going to write no charge. Okay, so protons have a positive charge, electrons have a negative charge, and neutrons have no charge. So one of the questions that I wrote here is which particles make up the nucleus? Now that is the center portion right here in the atom. So the particles that make up the nucleus are your protons, and I'm going to write plus neutrons. Okay, so protons and neutrons are in the nucleus. Now these particles orbiting the nucleus in this animation are the electrons. So what you have here is a nucleus with a positive charge and negative electrons orbiting around the nucleus. Now it's the positive charge of the nucleus that prevents the electrons from flying out into space, because positive and negative charges attract. So here we have a part of the periodic table. Okay, so let's take a look at this. We have the atomic number on the top, 6 in this case. We have the symbol for the element, C, which stands for carbon. There it is. Then we have the atomic weight, 12.01 in this case. So let's talk about what atomic number and atomic weight are showing you. So atomic number is the number of protons in an element. So atomic number is the number of protons in an element. Okay. Now, one thing you need to remember is the number of protons that an atom has determines which element it is. So I'll repeat that for you. The number of protons that an atom has determines the type of element that it is. So carbon always has 6 protons. If an atom has 6 protons, it has to be carbon. Okay. Now, atomic weight. The atomic weight is the number of protons plus the number of neutrons. So number of protons plus the number of neutrons. Okay? Now, if you know the atomic weight of an atom and you know the number of protons, then you can determine the number of neutrons. Okay, so in the case of carbon, the atomic weight, we'll just call it 12. The atomic weight is 12. The number of protons is 6. So your number of neutrons is 6. 12 minus 6. And this is an important point because the periodic table gives you a list of atoms, and the number of protons always equals the number of electrons, which equals the number of neutrons. Okay, so when you are looking at the periodic table, if it gives you an atomic number of 6 protons, then you know carbon also has 6 electrons and it also has 6 neutrons. Okay, so we'll say number of protons I'm going to abbreviate this, equals the number of electrons, remember E minus is electrons, equals the number of neutrons, which is actually just N, but I'll write neutron out. We'll abbreviate it like that. Okay, the number of protons equals the number of electrons, which equals the number of neutrons. And this is an important concept that will come into play later when we're talking about chemical bonding. Now, I put questions in this PowerPoint, and I want you to read the question and try to figure out the answer. Now, if you view your PowerPoint in with the notes section on it, so you would have to go to the PowerPoint that I posted in Canvas, not this one, because this is just a recording. So go to the PowerPoint I posted in Canvas. Under the View tab, you hit Notes. So what this does is when you look at my slide, underneath you will see the notes, and I've put the answer to the question. So an atom's blank are found in the nucleus. Your answer would be A, neutrons and protons. It cannot be electrons at all because electrons orbit the nucleus, and the nucleus has neutrons and protons. Now remember, the weight of the nucleus is protons plus neutrons. We don't talk about the weight of electrons because they really don't have much mass. They're extremely small. The other reason you should review these questions is I use a lot of these questions that I put throughout the PowerPoint in quizzes and tests. So it's good to remember them. Okay, now we are going to talk about isotopes. Now, an isotope is the version of an element, I should say, that has different number of neutrons. So let me write that out for you. So it's different versions of an atom Now remember, this is of a given element. So I'll put actually different versions of an atom of a given element. With different numbers of neutrons. Okay, so that is the definition of an isotope. Different versions of an atom of a given element with different numbers of neutrons. Now remember I told you that protons always have to be the same for a given element, right? Carbon always has 6 protons. So there are 3 different isotopes of carbon. This should have a 12 on it. Carbon 12, carbon 13, and carbon 14. Notice they all have 6 protons. If they have a different number of protons, they're a different element. So we say that carbon has 3 types of isotopes. Okay, carbon 12. 12 is the atomic weight. So there are 6 protons plus 6 neutrons. 6 plus 6 is 12. Carbon 13. Carbon 13 is the atomic weight. You know it has 6 protons, so now you can tell that it has 7 neutrons. 6 plus 7 is 13. Finally, carbon 14. 6 protons plus 8 neutrons. Okay, so carbon 12, carbon 13, and carbon 14 are all isotopes of carbon. They have a different number of neutrons. Now they will have different chemical properties because they have different numbers of neutrons. Like carbon 14, well, first of all 3 of these isotopes occur in nature. Most carbon in nature is carbon 12. There's maybe 1% or 1.5% of carbon 13 and 0.5% of carbon 14. Now carbon 14 is radioactive. That means it decays, it breaks down and gives off heat. So remember that an isotope is different versions of an atom of a given element with different numbers of neutrons. Okay, now here is a question that I'm going to go through with you because this is an example of a question I would give that is very applied. And what I mean by applied is I give you all the information in the question that you need. You have to put it together and come up with the answer. Okay, so let's talk about this. Earth's oceans are immense. Small floating organisms in the oceans called phytoplankton perform photosynthesis. If oceanic photosynthesis were to increase, what should happen to global carbon dioxide levels? CO2 is carbon dioxide. Now you may be thinking, but we haven't learned about photosynthesis yet, and that is true. But I give you the equation for photosynthesis in the image. So what this is showing you is carbon dioxide and water must be taken into a plant. A phytoplankton is like a little marine organism, tiny little marine organisms. So anything that performs photosynthesis must take in carbon dioxide from the air and water. Okay, so on the left side of your arrow, these are called your reactants. These are what go into a chemical reaction, which is what photosynthesis is. It's a process, but we also call it a chemical reaction. So, carbon dioxide, water go in, photosynthesis occurs, glucose, which is a sugar, plus oxygen are produced. Okay, so glucose and oxygen are what we call the products. And even if you didn't know the name for reactants and products, you can see that CO2 and water go into the reaction, sugar and oxygen come out. Now, I told you that oceanic photosynthesis increased. That means there are more phytoplankton, and therefore there's more overall photosynthesis. It doesn't mean there's more photosynthesis in an individual organism. It means in the entire ocean there are more phytoplankton, so now there's more photosynthesis. So what should happen to global CO2 levels? When I say global CO2 levels, I mean CO2 in the air. Or you could say atmosphere. I'll just say air. Okay. So there's more photosynthesis going on. So what that means is the phytoplankton, the organisms that are carrying out photosynthesis, there's many more of them now than there used to be. So they are taking in more carbon dioxide as a whole, right? The ocean is taking in more carbon dioxide. So carbon dioxide in the air, which is where these organisms get carbon dioxide, should go down. Okay, you have more phytoplankton in the ocean. They're all doing photosynthesis. So they all take in carbon dioxide from the air. Therefore, those carbon dioxide levels in the air should decrease. Now, this is a particularly difficult applied question, but it just gives you an idea of what an applied question is, right? You have to look at the information that's given to you and apply it to like a scenario. Okay, I'm going to end this recording at atomic structure. My next recording will be on chemical bonds.